So now before we talk about the different types of velocity the gas molecules can have, we can have different type of averages, not different types of velocities. Let us look at Maxwell's law of molecular distribution of molecular velocity. The law is derived from statistical thermodynamics by applying Maxwell-Boltzmann's law. So the law tells how the molecular velocities are distributed in a given volume of a gas. So here Fv, the probability function is plotted, that is the probability of a molecule with velocity v, and here v is plotted. So this is the relation, this is the probability. Maxwell showed that the speed of gas molecules or any molecule, gas molecules varies over a wide range. So the molecules are not just within this small range, they vary over a wide range. The probability of molecules having speed in a range of v to v plus dv is the area under the curve shown, that is that strip, so which I am going to draw. So this graph here Fv is plotted here and v is plotted here, and we get this curve like this. So this is the curve we get. So if we have velocity v here and this is v plus dv, so this is dv, then the area within this strip gives the fraction of molecules whose velocity, whose speed lies between v plus dv. That is the probability of molecules lying in this region is given by this area under the curve. This is the probability density. Fv is the probability density, which is a function, this function. So here essential part is the function contains two terms, one is quadratic and one is exponential. Initially the probability density function increases and then declines. So initially the function increases and then it declines. This curve is guided by two terms, the quadratic term and the exponential term. So initially for lower velocities, the probability density behaves as a quadratic function. That is, the first term dominates the exponential term for lower velocity. So when velocity is less, this term does not dominate, this term is dominating. So this is a quadratic curve initially, but at higher speeds, when v is large, this term is increasing, but this term is declining and this dominates more than this. But at higher speeds the exponential decay the exponential decay, this term, second term, that is the second term, dominates the, but at higher speeds the exponential decay, that is the second term, dominates the quadratic increase. As a result, the curves goes down. So now let us see that this probability density curve, how it responds to variation in temperature. So this is here V, and the probability density function is plotted here, and initially you see the curve increases and then it decreases like this. So it decreases like this. Suppose this is at temperature T1, this is at temperature T1. Now if we further increase the temperature, then the curve will be like this. This is temperature T2. If I further increase the temperature, the curve becomes like this. This is T3. So T3 is here more than T2 is more than T1. Here speed and here the probability density function is plotted. Now this is the probability density. So the probability of all the molecules within this total range is 1. So the area under the curve is 1. This is the total probability. If I denote in fractional number of molecules, then the area will be the total number of molecules. So now we notice here that if we increase the temperature, T3 is more than T2 and T2 is more than T1, then this point shifts here. So what is this point? This point, so this is the place where most of the number of molecules want this velocity, that is called most probable velocity. So the velocity which most number of molecules occupy I, that is called most probable velocity. Most probable velocity is the velocity for which the probability density is the highest. So let us define this as most probable velocity. This point is most probable velocity for temperature T1. You can see this is the most probable velocity for temperature T2 and this is the most probable velocity for temperature T3. So what we notice, thus we notice that with rise in temperature, the most probable velocity also increases. So when we increase the temperature of a system, most number of molecules which occupy the velocity, which we call the most probable velocity, increases with temperature. That we can see in the diagram. Also we see that the width of the curve also increases when temperature is increased, i.e., so the conclusion is, that is, more fraction of molecules now have more speed. So you see, as this width increases, that means now this type of velocity, that is the most probable velocity, previously the most probable velocity was suppose occupied by only 25% of molecules. Now 75% of molecules will occupy that velocity, this velocity range. That means higher, with higher temperature, the higher velocity are most probable are occupied by most number of molecules. So this is what Maxwell's law of molecular velocities is. Now based on this graph, we will see there are three types of average we can define for molecular, that is the average speed, next the most probable speed, and then the RMS speed of molecules. So now based on this probability density function of molecular velocities, we have three different types of averages for molecular speeds. So we can have three types of averages. So again let us draw this curve. Here we will plot V and here my FV, the probability function, and this is what the curve tells us. This is again that same curve that is found by Maxwell's distribution of velocities. So number one velocity is most probable velocity. So it is the velocity which is liked by most number of molecules. So it is the velocity where the probability is the maximum, that is the derivative here vanishes, the probability density is the maximum. So now let us see what is most probable velocity. It is the velocity which is favored by most number of molecules, that is where the derivative of this vanishes. So it is the velocity which is occupied by most number of molecules. In other words, it is the velocity, it is that velocity whose probability density is highest. So we know how to find when is the probability density highest, i.e. d by dv of Fv is equal to 0. So on this calculation of this, we get V probable as root over 2 RT by M, where M is the molar mass of the gas. If I am talking of a gaseous system, then M is the molar mass of the gaseous system. Now we know that molar mass is equal to mass of one molecule into Avogadro number. So I will write this. So this Vp becomes root over 2 RT by M into Na. That is, now R by Na is the Boltzmann's constant. So 2 kT by M, where M is the mass of the single molecule. So this is one type of velocity, that is the most probable velocity which I can define for an ensemble of gas molecules. Now, second type of average is mean speed of molecules. So, mean speed of molecules can be defined as mean speed of molecules is defined as V mean, we can say, or we can also use V average as suppose V1 plus V2 plus V3 plus dot 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 by total number of molecules I can do. So, this is what actually the average means, average of molecules. Now, here if I have to calculate V average, then V average is integral this V into that density into dV, that from 0 to infinity. So, this term if I will do with this calculation, finally we comes out to be root over 8 RT by pi m, where m is again your molar mass of this gas. This is for an ideal gas. If m is the molar mass, then these molecular velocities will be like this, and so V average will be given like this. This can be further written as again in terms of this K Boltzmann constant. We can write this as this term is equal to 8, this R will be R by Na will be the Boltzmann's constant K T by pi m, where m is the mass of each molecule. Now, this average velocity is, this quantity is greater than the, so you will get somewhere here this V average. So, V average is greater than the most probable velocities. Now, the third type of mean which we can talk now is root mean square velocity, also called VRMS. So, we define VRMS as root of, you can see it is root of mean of squares. Suppose V1 is the velocity of one molecule, V2 another. So, this is Vn molecule, so its average. So, this is the mean of square of their velocities, and its root is VRMS, root of mean of square of velocities. So, this is actually if we have discrete some number of, but for this probability function we define VRMS will be defined as root of, again, so you see this is root of, again this quantity will be integration of these V square terms FV dV. So, that on integration, if we will do this operation with this function here, then we will get this quantity as root over 2 RT by m, where m is the molar mass, and when I will write this as m the mass of each atom into Avogadro number, then R by Na will become K, and it will become 2 KT by m. Now, this is less than the previous one, that is the average velocity, and so you see it is here. So, this is VRMS. So, we see that VRMS is more than V average, which is again more than V probable. So, these are the three types of velocities of which we can talk in a gaseous system.